Hey students, my name is EMI-BRAIN. In today's class, we shall be looking at dielectrics and capacitance and dielectrics. In our previous class, we discussed extensively on capacitor, and we also looked at how to find the equivalent capacitance of a capacitor. Now, we define a capacitor as a device that stores electrical charges. So any device that has a capacity to store charges is referred to as a capacitor. Okay, but in today's class, our emphasis will be on capacitance and dielectrics. Capacitance is the ability of a capacitor to store charges, and this ability is dependent on the material called the dielectrics, meaning that if we are to increase the ability of a capacitor to store more charges, we have to introduce a material called dielectrics. And there are several materials that can represent a dielectric material. We have air, we have vacuum, we have paraffin, we have glass, right? We have ceramic, we have even thin sheet of paper can represent. Any material that can increase the capacitance of a capacitor is referred to as a dielectric material. But let's look at the structure of a capacitor. If we have a capacitor of this kind, a capacitor is made up of two parallel plates separated by a distance, right? By a certain distance, all right? Okay. Now, one thing you all should understand is that a capacitor remains uncharged until a battery is connected across it. So for me to charge this capacitor, it means I have to introduce a cell, a battery. Once a battery is introduced, there will be a transfer of energy which will be used to charge the capacitor. So there will be some charge distribution along the plate of a capacitor. Okay, now we have seen that a capacitor can only acquire charge when a battery is connected across it, right? But the capacity to store more charges is dependent on the introduction of what we call the dielectrics. That means if I'm to increase the ability of this capacitor to acquire more of these charges, I have to introduce a material which is referred to as a dielectrics. But in today's class, we shall be looking at air as a dielectrics and how to calculate the capacitance rather of the capacitor when air is the dielectric material. And from that expression, we shall also be looking at how to calculate or how to derive the formula for finding the capacitance of a capacitor when air is not the dielectric material. So follow me. Now look at this now. Remember I say that a capacitor remains uncharged, right? Until a battery is connected to it. But if we have air, let's say we are talking about air. If air represents the dielectric material, that means if, for example, we filled up here with air, we have air or vacuum, just an empty space. There is an issue with the use of air as a dielectric material because air at a higher voltage can ionize. Once air ionizes, the electrons in the air will escape. Once electrons escape, this will lead to the damage of the capacitor. But air can only be used as a dielectric when the cell is at a lower voltage. At a lower voltage, air is a good source of a dielectric material, or air rather is a good dielectric material. But at a higher voltage, air is not preferred. All right, guys. So let's look at how we can calculate. Don't forget that if we have a capacitor of a capacitor connected to an external source called the battery, the charge acquired by the capacitor is equals to CV, where C represents the capacitance of the capacitor measured in farad, V represents the voltage, while Q represents the charge measured in coulomb, V is in volts. Now, from this expression, we can deduce that our capacitance is equal to what? Charge over what? V. But for this, because air represents the dielectric material, we're going to be using the charge acquired by this capacitor when air is the material between the two parallel plates is given as Q naught equals to C naught times our voltage. Q naught equals to C naught times, okay, C naught times what? V naught. Q naught equals to C naught times V naught. Why are we saying that? The word zero represents the charge acquired when air is the dielectric material. C naught represents the capacitance of the capacitor when air is the dielectric material. While V naught represents the voltage when air is the dielectric material. When you compare that expression with this, what do you notice? Here we just have C equals Q equals what? CV. This represents what? The charge acquired for all the dielectric material. It can be plastic, it can be ceramic, it can be paper and all that, right? So we just use the normal symbol, which is Q equals to CV. Okay, guys, now look at this here. Let's look at this diagram here. In this diagram, we can see that we have air in between the two parallel plate capacitor. We have our battery and all that. Then the charge acquired equals to Q naught equals to C naught times V naught, right? Now, as long as there's a charge acquired there, the charge will create a flux called electrical flux. Are you there? According to Gauss law states that if we have a single system where there's a charge in that system, if there's a charge in this system, that this charge will create what we call electrical flux. And the flux generated by the single charge, the flux generated by the single charge is equal to the charge itself divided by permittivity of free space. That same is equals to what? EA. Okay? So for this, there is a flux generated from this charge system here. What is flux? Flux talks about the amount of few lines generated by a single point charge. The amount of few lines generated from a single point charge is called what? The electrical flux. The flux talks about the intensity. If I have a test charge here, let's say I have a test charge here. If a test charge is placed alongside with this other point charge, the test charge will experience the influence of the flux generated from here. The flux, F-L-U-X, generated from here. Okay? It's like saying if we have a burning bush, in a burning bush, by the time you apply your kerosene or your water or your fuel, what you notice, the bush will increase and you are going to be feeling the intensity from that burning bush. That means that what you are feeling there is the flux being generated from the burning bush. So the more we add more fuel, the more we experience the strength of that fuel. Okay, so charges, what charges does is that the more we add more charges, the more the lines of flux and the more the flux generated. So as long as we have a charge system here, there will be some generations of what? Of few lines out of this system. And that few line will create a flux, which is called what? Electrical flux. And according to Gauss's law, Gauss law says that the electric flux generated from a single system, is equal to the charge enclosed by that system divided by the permittivity of free space, which is also equals to what? EA. Also equals to EA. Let me repeat myself again. The flux generated from a system is directly proportional to the charge enclosed. The charge enclosed there is our Q naught, right? Divided by the permittivity of what? Free space, which is also equals to EA. E represents the strength of the field. Okay, but E, the strength of this field we are referring to is also known as what? E naught, because we are dealing with our charge when air is the dielectric what? Material. Okay? Alright. Don't forget that your strength of the field depends on the flux. The more the flux, if the flux increases, the strength will also what? Increase. So increase in flux generated from a single point charge leads to a corresponding increase in the strength of the field. So this is what Gauss law is actually stating. So from here, we can cross multiply this to get our Q naught. So Q naught becomes E naught A, permittivity of free space. Let's call this equation 1, this equation 2. Okay, from equation 1, you notice that equation 1 says that Q naught equals to C naught V naught, right? Equation 2 says what? Q naught equals to E naught A, permittivity of free space when air is the material. So I can equate these two together meaning this can be equals to this. I can say equate equation 1 and 2. By the time we equate them, that simply means that our C naught V naught should be equal to E naught A permittivity of free space. So if we equate these two together, we can from here determine the capacitance of the capacitor when A is the dielectric material, which is our C naught. So what we do is by dividing both sides by what? By V naught, right? To divide both sides by V naught, that means our C naught then is going to be E naught A permittivity of free space divided by V naught. Okay. Now there's a relationship between potential difference or your voltage and your intensity relationship, or recall that V is equal to what? ED. V equals to ED. This is the relationship connecting voltage and what? Intensity. Voltage and intensity. But because we are dealing with air as a dielectric, here is going to be our V naught equals to E naught, right? The same distance is being maintained as D, right? The same distance is maintained as D. So I can actually substitute the value of this into this expression here. Therefore, we have that V naught, C naught rather, equals to what? E naught A permittivity of free space divided by E naught times what? D. This can go with this, right? So our capacitance of the capacitor when air is the dielectric material is then equals to what? A permittivity of free space divided by what? D. Please take note of this. This is the formula for finding the capacitance of the capacitor when air is the dielectric material. Okay, this we call this equation. This equation 2. This is equation 3. This is equation 4. Then this is equation 5. All right, guys. Now, when the capacitor is now filled with a dielectric material, the capacitance of the capacitor will change. I hope you are aware. You know, here we are talking about when air is the dielectric material. Now, when air is now being replaced with a different dielectric material from the capacitor. You know, before we are talking about air, right, as a material. When we now remove air and replace air with another material, let's say this time around plastic or any other material, it simply means that this expression will change. It means that the capacitance will change. Are you following now? The ability to store more charges will change. And the capacitance of the capacitor then will now become K C naught. Because why? We have been able to replace air with a different dielectric material. Now, this represents the capacitance of the capacitor when air is not the dielectric material. C naught represents what? The capacitance of the capacitor when air is the dielectric material. The value of K represents the dielectric constant. What this implies here is that for me to actually remove air, I have to put what? A material, and that will give us a what? A new capacitance. Now, from this expression, we agree that our C naught is equal to A permittivity of free space divided by D. By the time I replace the whole of this in this expression, that means I'm going to replace this into this expression, and that will give us our C equals to K A permittivity of free space divided by what? By D. This is called the capacitance of the capacitor when air is not the dielectric material. The value of K represents the dielectric constant. The dielectric constant. Okay. A represents the area of the capacitor. E naught represents the permittivity of free space. The permittivity of free space, which is about, and this is about 8.85 times 10 to the minus 12, right? Okay. Then D represents the distance separating the two plates. So this formula is the formula that should be used to calculate the capacitance of the capacitor for other dielectric material. Although we can still use this for that of what? Air. Because I say that the dielectric constant for air is equals to what? 1. Air has a dielectric constant of 1, likewise that of what? Vacuum. So if I'm to substitute this K as 1 into this expression, I will still come back to this, right? Because 1 times A times our E naught times Z will give us this expression here. So that means that the capacitance of the capacitor is given as what? As this. Please take notes. This is the formula for calculating the capacitance of any dielectric material that is being placed in between the two parallel plates in a capacitor. Okay, let's look at the effect of dielectrics. The first effect is that it increases the capacitance of a capacitor. From our expression we derived, we saw that C is equal to K, permittivity of free space times area divided by Z. What you notice that capacitance and K have a direct relationship, meaning that if I'm to introduce a dielectric material in the capacitor, it will increase the what? The capacitance. Are you following? By a factor of what? Of K. Now you can see that the capacitance and the constant K have a direct relationship. They are both directly proportional to each other, meaning that if we are to increase or add a dielectric material to a capacitor, it also increase its capacitance. But don't forget that our permittivity of any material is equals to K times what? Permittivity of free space. Meaning that if we are to determine the permittivity of any other material, which is not air, the formula is simply by introducing the dielectric material, which is our K, into the capacitor that has air, right? As a dielectric material. So if we introduce the material into a capacitor that has air, that will give us the permittivity of that material that was introduced. So from here, that means that the value of our permittivity of any material is equal to K times permittivity of free space. So if we are to replace this expression you are seeing here is simply this. It's simply this with this, right? It's simply this. That means our capacitance can also be given as permittivity of any material times area divided by what? By the distance. The permittivity of any material multiplied by A divided by distance of separation. Number 2 is that it helps to increase the charge stored in a capacitor. If we put a dielectric material into a capacitor, it will help to increase the amount of charges that will be stored because from what we say there, dielectric helps to increase the capacitance. And what happens there is that the amount of charges is also increased. From our expression we derived, we saw that our Q naught equals to C naught V. We also saw that our C equals to K C naught. So from here we can make our C naught as the subject of the formula, and that will give us C naught equals to C divided by K. So by the time we put this value of C naught into equation 1, this will give us our Q naught equals to C over K times V. So C times V is actually CV divided by what? By K. Okay? This is like saying over 1, right? So from here, our C times V is CV equals to K Q naught. Don't forget that C multiplied by V represents charge. Charge equals to K Q naught. Okay, from this expression, we can see that introduction of what? Our dielectric material actually helps to increase the amount of charge because these two, they are what? Directly what? Proportional to each other. The third one is that when you introduce a dielectric material into a capacitor, it lowers the voltage of the capacitor. The fourth is that it also lowers the intensity or the electric field of that capacitor. Don't forget that we say that electric field intensity and your voltage, they are both directly proportional to each other. And the formula connecting them is equals to V equals to what? ED. Meaning that increase in intensity leads to increase in what? In voltage. So whatsoever happens to intensity or your electric field strength also happens to what? Your voltage. So that material lowers the voltage. If it lowers the voltage, that means it must also lower the electric field intensity. Thank you.